Maybe also showing you how you open it. So if you go to into this folder called NAM Calibrator, and then inside is then an application file called the same NAM Calibrator. If you double a model that has been set up but which is not calibrated, right? And what we do is just the open icon up here, and then there's an example, and under that example 1, and there's only one in this one called exercise NAM. And if you open this, it should look like that. It may give you a warning like it does on my computer, but that doesn't matter. What we see here is then at the bottom the graph. There are two hydrographs. One is the measured discharge and the other is the simulated at this point. And then the inclining graphs in yellow and green are the accumulated flow of these two. So there are a number of parameters. Actually, the area is also there, but of course the catchment area you don't change as a parameter, but it's part of a model, right? So a number of parameters. There's these Umax, Lmax, for example. This is upper storage and the lower storage, which has an impact on evaporation, different coefficients and so on. And you can see them up here as numbers, and you can see them over here as slides. So if I grab one of these and change it, you can see the curves are changing, right? So it does the calculation on the fly and changes the condition. So this one is changing the accumulated and, of course, the graph itself. You can zoom in down here just by making a square and then see details for that particular year. If you right-click, you can then unzoom, and then it goes back like that. So your task is to change the different parameters over here. And down here at the bottom is a correlation coefficient and a coefficient of determination. These are measures of how well your graphs are matching. There should be, I don't know, did you look at that on your desktop, whether there is a NAM short description? I don't know, I'm not sure it was copied to the computer. Otherwise, we'll just get it on the stick for you. Because that includes a brief description of what is actually the impact of the different parameters, if you want some guidance. But otherwise, you can also just get going. Because if you grab one and change it, you can see what it does to the graphs, right?
A particular combination of all the parameters is sure to fetch me a coefficient of 1?
No. If a coefficient of 1, there will be absolutely no difference between the two graphs at all the time. And that's not possible. Or the only way to do that is that you set up a model, you run it, and then you take the result of that as the observed discharge, and then you can measure it again. But this is a real case from the real world, and nothing's perfect out there. So I'm just displaying, if you can read that, a brief description of the main parameters that we will mainly be working with. But that is from the short description, which is with a bit of luck on your computers already. It wasn't working all the computers. No, this computer has a problem. They fixed it yesterday. Maybe or maybe you have to join somebody. But let me see if I can find somebody who can fix it. There's the computer over there has the same problem as yesterday. If anybody. Well, I mean, both to increase, but let's go for the second one. Let's go for the coefficient of determination as sort of the I mean, none will reach 1, but as high as possible. Let's choose the coefficient of determination as the one we're trying to maximize, right? Simulate and observe by changing these different parameters. And some inspiration can perhaps come from the description of what they are, the main ones. and in the real model, we have this auto calibration tool. You press it and then it's there, right? But it's not, for you, it's not so easy. And the idea here is to get the feeling of when you change it, like take the Lmax. This is the storage in the root zone. So how much water can we have in the root zone? If the root zone is very small, how does that affect the water balance? If it's very large, how does that? So what you can do is taking them one by one, go a bit up and down and see how does that actually change the curve and get some feeling for what is the impact of this. Because these some parameters affect the same things, right? But in different ways. And then the blue, which is been measured, right? Those are the ones it's calculating the coefficient from. And this is just the accumulated water balance, which also matters, right? But it's not the main thing, right? So, and one difficulty here is that when you change this parameter now, you might find this is where you have the maximum, but then when you change some of the others, you may come back and find, then again, this needs to be changed, right? So it's not so easy.
It's not so easy, that I'm doing.
We then have peaks and we have base flow after that. A coefficient like the overland flow coefficient here, CQOF, if that becomes smaller, then we don't change so much the volume or runoff in total, but the distribution between peaks and base flow is changing, right? So you can see how, even though it's called an overland flow coefficient, it also impacts the base flow. Right? And that's typical in all this type of model. Whenever you have these, you typically have these coefficient that determines peak sizes or volumes. That's what happens. Peaks are determined both in their in this volume, but there's also the timing, and here is one controlling the timing. So if you can route the peaks faster or slower like this, right? So something like that is where it should be matching. Another issue is that we see in many of these years that in the beginning we're not really it's not matching. It's matching better later in the wet season than in the beginning of the wet season. And there are threshold values. We discussed that a bit yesterday. This threshold value that would be 0 if the catchment was very inhomogeneous, but have some value if it's more or less the same soil and so on. And if I take that one and increase it, you can see that it affects mainly the first peaks and not so much the later peaks. So like that, the idea of this was to get an impression of when you change parameters, how does it actually affect? And like I said, all these rainfall runoff models are quite similar in structure. So if you work with another model, the same type of parameters will be there.
But are there models that can do it automatically?
Yeah, I mean, there are the official NAM model we have in Mike 11, there's this auto calibration. And when you push that, it just, but the auto calibration is not a hydrologist. It just matches curves, right? And if there are data issues or other issues, it won't discover that, right? So you don't get the perfect model from an auto calibration. Another thing we also illustrated, I think, by this case is that it will not be perfect. I mean, here this year is matching quite well, both in volume and all, but here we can see that the accumulated is deviating, because in this other year, we're then simulating too much. And if you fix that, then you'll be simulating too little in the year before. So often it's a yin and yang thing that you can't get it perfect, right? And that's nature, that's the way it is. So when you're calibrating, you should also consider, why am I doing this? What is the purpose of this? If this is flood forecasting, well, then we want the peaks to match. If this is to, if you're setting up a reservoir, maybe downstream this location somewhere, there's a plan for a reservoir, and they have measured the discharge for 3 years. That's not a very good basis for designing a whole reservoir, but that's the only data you have of observed discharge. What you do is you calibrate it, and then you focus on getting the volume correct, right? The volume over these 3 years. And then you take your 50 years of rainfall and generate 50 years inflow series. And then that is probably a better estimate of both the average inflow and the variation between wet and dry years than just these 3 years. Right? I think we're breaking for tea, and then we meet somewhere else.
Yeah.